from the MUSE Atlas of Disks survey. Last year, my colleague Mark Den Broek came here to, came here to give a talk and presenting the survey. And today I'm gonna present you the first results of the MUSE Atlas of Disks, MAD. So first, what is MAD? MAD? MAD is not this, or at least it's not what I'm gonna talk about. Then this is not either. This is what you find when Googling MAD. But MAD is a survey, an ongoing GTO survey with the MUSE instrument on the VLT telescope in Chile. It's a GTO program led by Marcela Carollo in Zurich. It aims to observe around 50 nearby galaxies that are in the Staphome main sequence, and with half stellar masses between 10 to the 8 and 10 to the 11.5. And all of these galaxies have HST data. Then the sample is composed by, as I said, around 50 galaxies. So far, we have observed 34 galaxies. And the first results that I'm going to present today are about these 34 galaxies. And here is how they lie in the Staphome main sequence region in the Redshift 0 universe. And with this MUSE data, we're gonna get around 100 parsec scales on average. And now I'm gonna talk to you about what is this physical scales. So this is one of our galaxies, NGC 1309, a beautiful spiral galaxy. And this is the field of view of our instrument of MUSE, which is one by one arc minute. And this is how it would have seemed with one of the previous IFU surveys with 1 kiloparsec resolution. And now with MUSE, we're able to break these scales and get to way, way lower spatial scales around, in this galaxy, 25 parsecs, for example. And inside this square that is 1 kiloparsec, you can identify two very distinct regions. This is a Staphome region with a very strong emission lines, and this is a old stellar population region with continuum and absorption line spectra. So today I'm going to talk to you about the first results from the first papers that are MAD1, which describes the survey. It's Carollo et al. MAD2 is the paper by Mark Den Broek, talks about the stellar and ionized gas kinematics. My paper talks about the physics of ionized gas at Redshift 0 disks. And then finally, the first paper of this series is, the last paper of this series is MAD4, which talks about the stellar populations of these galaxies. So let's start having a look at the first results of MAD2, which is Den Broek et al. Deals with the stellar and ionized gas kinematics. I'm just showing here beautiful stellar velocity maps of our 34 first galaxies, ordered in increasing mass towards the bottom of the figure. And you see here, this is a stellar velocity map. There is a lot of substructure, and as we go to higher masses, there seem to be like pinched velocity fields that correspond to inner disks that are being formed. And this, for example, wouldn't have been seen with previous IFU surveys with lower spatial resolution. Then also when we look at the stellar velocity dispersion, we see that some of these disks have lower velocity dispersion than the surroundings. But also in general, we see that the velocity dispersion is increasing with stellar mass. Then I'm going to briefly mention some of the results of MAD4, which is the stellar populations, led by Masato Onodera. Here in this movie, I'm presenting like the typical 4-plot figure with the continuum color composite images, a stellar mass surface density map, and the stellar ages and the stellar metallicity. So with these 34 galaxies, we have a lot of different substructure information, a lot of, these galaxies present different properties like barred galaxies, non-barred galaxies, galaxies with bulges, galaxies with non-bulges, with classical bulges and pseudo bulges, etc., etc. And we see very different behaviors from very different galaxies. Now I'm going to talk about the results from my paper, which deals with the physics of the ionized gas, which are the extinction, star formation rate, and metallicities. This is a typical figure for one galaxy, NGC 289. That is a beautiful spiral galaxy, as we see here in the narrowband image that we have created with the strongest emission lines. And I've presented here the stellar mass surface density map from the continuum, where we see that there is a bar and apparently a bulge, a dense bulge in the center. So from the H alpha and H beta ratio, we can derive the extinction with the Balmer decrement. Then we compute also the star formation rate density, the resolved star formation rate. Then we can get to know how our regions, this is the map of our regions color-coded by the BPT diagram. We can get to know each of our regions, what is the ionization source. So this is the BPT diagram. Remember, this is the star forming region, and this would be AGN shock or layer or whatever you want to call it, region. And now we have created a BPT parameter that we've called eta, that just goes from the star forming to the red part, and it's it depends on the distance to this point to these two lines, and this is just to see in the 2D map like the position of these regions in the BPT diagram, so that the blue would correspond to the star forming regions. Here, for example, the spiral arms we see, and the AGN shock part that is in red in this plot. Then we have also computed gas metallicity, the gas metallicities for our galaxies, and finally we're also able to disentangle or distinguish between the diffuse ionized gas and the gas that is in compact regions in the so-called H2 regions. Now I'm going to show you one individual story. That is what happens when we combine all the information from the different papers. For example, from my paper in this galaxy, you see in the star formation rate map, you see an inner ring that is star forming, and also like an outer ring that is formed when the two arms close. And what happens when we relate this information with the information of the kinematics from Denbrock et al. For example, this is the stellar velocity dispersion map, and we see that our inner ring has has colder or lower velocity dispersion than the surroundings, but also lower than the center. Then this is the gas velocity map of this galaxy, where we see also there is different behavior in this part. And what happens when we model the velocity and subtract it to get to know the deviations from the circular motions? This is what we know as the gas residual, or the residuals from the velocity. That is the deviations from the circular motion. And here in red, we see that these regions stand out. And if we compare this to the BPT diagram, we see that there is a very well correspondence between the red in the two. Here red means the higher deviations from the circular motion, and here red, remember, means the AGN or shock. So we see, for example, that maybe this gas that is deviating from the circular motion is in a shock region. Then also what happens when we look at the gas metallicity map, we see that these regions with higher metallicity correspond also to the regions that are deviating from the circular motion. Now we're gonna look at how the metal enrichment is produced in these local scales. So for that, we look at the gas metallicity gradient, which is the gas metallicity as a function of the galactocentric distance. This is for our 34 galaxies here. And we see that the metallicity gradients are declining, which means that the metal is enriched in the centers and goes down as far as you leave the center. This is consistent with an inside-out scenario, for example, inside-out growth. However, I want to call your attention because with this data we can have very good idea of what is going on in local scales. And when you azimutally average to produce the gradients, you lose a lot of information. For example, these are the 2D maps of the metallicity of these galaxies. For example, here you see that the inner spirals are more metal enriched than the spirals in the outer parts. For example, in this galaxy is the one we were seeing before with highly metal enriched liner emission. This is for example, the galaxy that had a star forming inner ring. Here you see, for example, the very metal enriched H2 regions in the bar. Here you see, for example, inflow or outflow of high metal enriched material to the center. And here, for example, this galaxy is a merger that presents like distinct components of metallicity, but when you average azimutally to produce the gradient, you get a flat gradient. Now, in order to continue with the study of the local enrichment, of the local metal enrichment, we're going to look at how the metallicity is related to the stellar mass. So now, remember, we we know that in a global scales, the metallicity is correlated with the stellar mass, with the total stellar mass. And now we're gonna see if this relationship, the so-called mass metallicity relation, holds for these local scales. For that, we have plotted here the information for all the regions from all the galaxies, all the 34 galaxies, and we see that there is a very well correlation between the gas metallicity and the stellar mass surface density. We see also that this slope flattens at around 10 to the 3 in these units. Now, to understand better why this is happening, we're gonna look at the dependency with the total stellar mass. So we're gonna divide our 34 galaxies in 3 mass bins, which are these 3: the lower mass bins with stellar masses below 10 to the 10, the intermediate mass bin galaxies with stellar mass between 10 to the 10 and 10 to the 10.8, and the high mass galaxies with total stellar mass above 10 to the 8. We see, first, we see that this slope flattens, and secondly, we see that the range of metallicity change. Like for the low mass galaxies, the range of metallicity is between 10 to the 7.8 and 8.7, and this is higher, like between 8.3 and 9.2, and this is even higher between 8.6 and 9.4, for example. So we see, or we think that this is because the local enrichment depends on the total mass of the galaxy, which is that the local enrichment depends on the potential well of the galaxy, and as our galaxies grow in size and mass, they also become more metal enriched. Now we're gonna look at how, if there is a relationship between the stellar mass and the star formation rate. As we know, for global studies at low and high redshift, we've seen the star formation sequence, and we're gonna see if this holds at local scale. So we're gonna present now the regions for all the galaxies as before in the star formation rate density and stellar mass surface density plot, and we see that there is a correlation. There is a resolved mass star formation rate relation at these scales. Then what happens when we divide in stellar masses as before? We don't see the same as we were seeing before. For example, for this stellar mass surface density, we see that there is a wide range of metallicities. And also this slope doesn't change dramatically as it changed before. So it leads us to think that the metal enrichment is not the same process as the formation of stars, and maybe the formation of stars depends more on the availability of gas than the local enrichment. And these are my math conclusions, and thank you. I can hear you, sorry.
I'm going to shout. I'm just going to say this is like obviously an amazing data set. I just wanted to call to your attention the fact that metallicity calibrators are not meant to be used for finer white gas. So saying high metal enriched finer white gas doesn't mean, because as you know, with different calibrators for finer white gas, some of them will overshoot the metallicity and some of them will be lower than what we otherwise get. So unless you calibrate for different fractionation states of gas.
Yep. So I agree completely with you. Of course, I haven't been able to go into details. In the paper, we use different calibrators for this analysis. We've stayed with Dopita et al. Calibration that it can be also used for different ionization ratios. But also, I am able to show you, if we believe that, for example, where is this in here? If we believe in if we can measure the metallicity of the diffuse ionized gas, for example, there is still a mass metallicity relation that it would hold for both diffuse ionized gas. But also, like, I mean, when we restrict to H2 regions, this is what we find. We find the relation that we were finding before. I mean, I agree completely. And also, like, these metallicity gradients also change depending on the calibrator that you use. No, I mean, I agree with what you said before about the metallicity calibrators.
Have you checked if there is any difference between barrel spirals and the spirals without barrels? We can know that probably the spirals behave differently, the barrel spirals than the ones without barrel, and also if you have any influence Chokes coefficient and the metallicity coefficient.
Sure. So in this paper, yet we haven't studied differently barred galaxies and non-barred galaxies. I can tell you that we find bars that have star formation that have a lot of H2 regions in their bars. We have also barred galaxies that don't have a star formation in their centers. And also this is a topic that has been studied well before and that is not solved, why some bars have H2 regions that are ionized and why others don't.
Okay, let's thank Santiago again.